Very good. So this is Advanced GR Lecture 1. There will also be a semester-wise plan on the web page. So let me again write the web page here. All notes and links will be available here.
And also regarding the assignment of
Yeah.
exercise,
Yeah.
how
Yeah, people who are not registered want exercises, or only people who are registered? Yeah, people who are registered should do exercises. I'll give you exercises. There are exercises in the notes that I'll be circulating. So one thing you can always do is to solve those anyway. We'll talk about it. I think you people meet me separately. We have to have a discussion on how to plan that. There will definitely be exercises. I'll also be very happy if people suggest exercises which could be added in the notes. Good.
So the website is not accessible actually.
Really? That is surprising. Maybe I haven't made it accessible. That's possible. It's accessible to some people. Or you've typed something wrong. I don't know. Try again. Okay. It should just show a landing page and there's nothing much more, but soon it will have more. Good. Okay, so why are we here? So in my mind, so something very interesting has happened in the last 10 or 15 years. As you know, probably it's been 40 or 41 years since string theory became very popular as a way to study quantum gravity, apart from many other reasons. But most of what you can do in string theory is to study some perturbative quantum gravity and some proof of concept that this is ultraviolet finite, and you can calculate things like graviton scattering amplitudes in simple backgrounds. But I think something happened after ADS CFT, which came much later in the late 90s, which is that this community, the people who started doing string theory were the particle physics community. There was also a general relativity community. And by and large, these two communities never talked to each other. So for example, I know I'm doing this again. I did my PhD in the late 70s, 76 to 81, and I did not hear the name of Stephen Hawking even once in Stony Brook. Because even though he had just written that paper, black holes radiate or whatever it's called, not even once, and yet this is the department where I did my PhD, where supergravity was invented. So there's a paradox, right? People are inventing supergravity and they're not interested in Hawking radiation. It can't be. And somehow I think this paradox, so one community kept working on physics of GR. It might be approximate, it might not be ultraviolet complete, but there's something you can do. After all, Hawking did all these calculations. And that community was very largely localized in Britain with many important offshoots. And of course, in US, there were notable people like Bryce DeWitt and Misner, Thorne, Wheeler, of course, people like that. They were also connected to gravity observations. While the particle physics people were basically focusing on CERN and the super collider and all that. And so they were completely separate communities. There was really no contact. And the contact then started to grow, and I think it was really, in a way, I may be wrong, it's a controversial view maybe, but I think it was really Maldasena's time that when he wrote this ADS CFT paper, that people were like, well, if we want to understand ADS CFT, it's high time we learned gravity properly, not just what gravity is taught to us in university, but as QFT people, we can't not know gravity. We have to now know gravity as well as we know QFT. And then people started burying into the literature and found that there was like 5 decades of research which they knew nothing about. And I would actually name one of the people who really did this on his own and then popularized what he learnt was Strominger. Andy Strominger, for example, had a really though he was a string theorist, he had a gravity background. Horowitz, Gary Horowitz, people like that, because they had been trained by a gravity person, not a particle person, or somehow they had got into that field. So then things started to merge, and now we are in an era where you cannot say that QFT or gravity, which one is more important. In fact, they are not even different according to ADS-CFT, so we better know both properly. But in the same era, last 20 years, people want to study quantum effects. It's very natural, that's the new thing, the new frontier. But people aren't trained in the classical physics of it. Now, how can you do quantum effects if you're not trained in the classical physics? That's not how we did quantum field theory. First of all, quantum field theory has the advantage that the classical physics, classical field theory without gravity, it's hard, but it's not earth-shakingly so. Maybe the hard things in that domain are like, fluid dynamics, effective description of classical field theory, and so on. But quantum field theory, as you know, is a really tough thing to do. And but the classic, it's not like any book on quantum field theory spends 10 chapters doing classical field theory. It might spend 1. Gravity is different. You can't do, even if there was a complete theory of quantum gravity today and you all wanted to learn it, I doubt you would get anywhere without all the topics I've listed here. And people like Juan Maldacena, but also many other people in the community really, burrowed into that gravity literature to learn what's going on. I'll give you an example. Prior to 1997, nobody in the QFT community could tell you what is anti-de Sitter spacetime. Nobody knew it. It was literally Maldasena's paper taught them that there is a thing called anti-de Sitter and we need to know it. At the time, there was still debate whether we live in de Sitter, anti-de Sitter, asymptotically flat. It was mostly thought that we would be asymptotically flat. So evidence for a positive lambda came a little later, and it took time to get people to adjust. But whatever cosmological constant we live in, no particle physicist has any reason to care about it. But now we really care about it. So you see, the whole subject has changed. ADS and DS have become very central in the subject, and learning gravity, which is the real physics of space-time, of curved space-times, has become a thing which it was, I would say, much less in our community. So this is the underlying motivation. And I'm going to keep this course classical because all the classical stuff that I'll be telling you is all correct, and many of these things have experimental implications and they are tested. As far as we know, all black holes in the universe are curved black holes. Whenever they have tried to find out what the angular momentum of a black hole is by reconstructing LIGO data, they find that it seems to be something like 0.5 or 0.7 of the maximal value, which is fabulous, right? Because if it was on the other hand close to 0, then we may not need a curved black hole. It would be like nearly Schwarzschild, but it's actually highly rotating. 3/4 of maximal is really a very rapidly spinning black hole. So we need all that. So that's the substance. Good. Any questions? These were very general comments, maybe a bit rambling, but any questions or comments on that? Please look a little more relaxed and do a little more talking. Okay, people have relaxed at least. Okay, conventions. We need conventions to do these things, and they are all in the notes, so I won't bother you too much, but just to emphasize a few things. So obviously the fabric of our subject is called space-time, and it's a differentiable manifold. In d dimensions, so d is total dimension always for this course. With a pseudo-Riemannian metric. Pseudo is the word we use for the fact that metric has got a negative eigenvalue for the time direction. And the signature is minus plus. Okay, that, and Under reparameterizations, this signature will be preserved. There's one more thing. You also have to say that the manifold is time oriented. This is really important. This is something that you don't have to say in ordinary Riemannian manifolds where there is no such thing as time. Time oriented means that there is a notion of future and past. And that it's preserved under changes of coordinates. We'll be doing these. We'll be visiting these definitions again much more carefully in the causality section. For now, this is just a working definition. There's all kind of stuff like Hausdorff, paracompact, and so on. I don't want to spend a lot of time on it, but right now I want to spend zero time on that. This is good enough. Okay. Physically, the idea is that if a vector is pointing like this, then it's future directed, and if it's pointing like that, then it's past directed, and if it's pointing that way or that way, it's space-like, and we don't really care. Most of the time, we don't care. Okay, a few things like symbol, yes.
So, is there a simple example for a non-time oriented pseudo-Riemannian manifold?
Oh, absolutely. I think you can simply have a, well, time oriented, sorry, yeah, good. There is, but whether it's simple, I can't think right now. Can anyone think of a non-time oriented Riemannian manifold? I even thought I'd given an example, but Klein bottle type of thing comes to mind like the most likely thing.
Anything with a closed timeline.
No, so closed timeline still has a sense of past and future because it's about the direction of the arrow. So even if there's a closed timeline curve, of course the manifold is bad for various reasons, but I can still say I'm going in the future. Even here I'm going towards the future. It's about the direction I'm moving in. So here I am in the past of where I started, but I'm still moving towards the future, and I can also reverse my motion. So it's like at any point I can always have a sense of future and past. But you can have manifolds where somehow this and this light cone meet in some continuous way, and then you don't have that. Okay, I'm going to skip all definitions like Christoffel symbol, covariant derivatives, etc. I will use this symbol for covariant derivative, and just to write one formula. There are two formulae, I'll write both. It's really good to commit them to memory, and I'm sure many of you know this backwards, but the fact that, so the formulae that involve Christoffel symbol have the nice property that they are easy to memorize, including the definition of gamma. The formula with Riemann tensor not so easy to memorize, but one can still.
One thing, the manifold is torsion free, right?
The manifold is taken to be torsion free, and the connection is the Christoffel symbol, which is symmetric in its lower indices. By the way, since you asked that, torsion, which is the antisymmetric part of the affine connection, is a tensor. Now, if it's a tensor, it's not needed in order to define a covariant derivative. It would be what we might call a non-minimal term. Nobody stops me saying plus a tensor times V. Okay. Now, if I have, but it's an independent field. It doesn't come from the metric anymore. Only this part of the Christoffel symbol comes from the metric. Now, if I'm going to have an independent field, and here is where the difference between relativists and particle physicists comes in. Particle physicists are quite aware that if we are studying gravity, we are going to someday couple it to photons and gluons and fermions and scalars. Relativists in some way have, I don't say that they really believe it, but have sort of taken the attitude that pure gravity is a subject. Of course, it's not a subject, right? It's a field theory. You can couple it to any other field, and you are only doing a special case if you don't couple it to another field. So this digression is to say that if you have torsion, just treat it as another field. In that case, you don't have to ask that question anymore. This, by the way, this is something I learned from the supergravity people. So there are a lot of interesting things happened in gravity during the supergravity discovery era, which is that they understood from a field theory point of view many things which gravity people had not properly understood. One of them is how to couple fermions to gravity. It's amazing that there was almost no literature on that till supergravity came around, and they had to invent that literature. We'll come to it. Okay, just to write one more formula quickly. Covariant derivative commutator acting on a vector. So I'm assuming people know how vectors transform, for example. Lower index, upper index, covariant, contravariant, that's all part of the basic stuff. But for example, here you have R, beta, alpha, mu, V, beta. So these things start to become difficult to memorize. It's different on a lower. It's different on a upper. No, this is wrong. I just wrote something wrong. I read the wrong one. First is V lower, yes. Beta alpha, yes. V beta. So right. And here it is R beta alpha mu V. And this is very important, as I'm sure you know, the commutator of two covariant derivatives measures second order deviation from a point in space-time, and that is what gives you a measure of actual curvature, because first order deviation in some sense is trivial. It's very coordinate dependent. You can even find coordinates when the Christoffel symbol vanishes at a point, but you can never make its first derivative vanish at a point. We'll get into all these things later. Then there are all the symmetry identities on Riemann tensor. I'll leave that. Now we'll just be going very briefly over most of these things just to make sure that we are, as they say, on the same page. But unfortunately my eraser, which was a dirty piece of cloth, where?
Dust. Yeah.
Ah, here. There was also cloth. I think it's gone in the corner. This
So
will
the acting will be V beta.
yes, this will be. Thank you. Good. Okay. So now we have to talk about two kinds of objects on manifolds. There's nothing new in this discussion special to pseudo-Riemannian. So it's just a matter of establishing notation. I've actually introduced vector fields already there, their components. But just to use the formal notation, V will stand for V upper mu del by del x mu. And the reason, and these are local functions, when I write x without anything, it means all the d component coordinates. And this means that we think of a vector as a differential operator, which acting on a function differentiates it and multiplies it by the component V upper mu. And the reason to do this is that there's an intuition that when I have a vector field, let's say that I know magnetism and I know the lines of force of a magnet, then I think of those lines as generating a flow. Okay? So from any point in the region of a magnet, I can flow along the line of force to the immediately infinitesimally neighboring point. So this embodies that idea, because if I have a function f at a point, I can take v on it and get a new function v of x, which is just v del by del mu, which is actually v mu del mu f. And this is the change of f if I flow a little bit in the direction of the vector field. But there's a very nice feature of this notation, which is that v does not change under any change of coordinates. What does change is this by chain rule, and therefore this changes by the rule which you all know of transformation of contravariant vector fields, such that this product is unchanged. So actually, if we were working with these, then we are talking of coordinate dependent things. But if we keep working with these, then these are coordinate independent things. And for a physicist, often this is just a notation so that you can remember how V transforms. If you forget some one fine day on a desert island, you can remember chain rule. Surely we all remember chain rule. It will tell you how V upper mu transforms. So that's a vector field. I will also use short forms like V mod squared, and I'll call it V dot V, and it just means V mu, V mu. The components contracted. In this notation, we see that it's coordinate invariant because the indices are contracted. In this notation, it's coordinate invariant because V is coordinate invariant quantity. This also should be thought of more properly as G mu nu, V mu, V nu. Actually, this is not such a good thing to write in the beginning. That's the correct thing to write because V is only defined with mu up. V lower index is brought down with a G. Good. That's the norm, and I'm sure you know that if V dot V is greater than 0, then it's called space-like. If it's equal to 0, it's called null. If it's less than 0, it's called time-like. And null vectors are frankly the single most freaky thing about pseudo-Riemannian spacetimes. There's no analog in normal spacetimes, and they have such weird properties that even now I kind of wake up in the middle of the night shaking because I'm still confused about something. For example, consider a null vector normal to a subspace. It also lies in that subspace. It's really annoying. You just can't get it into your head. I mean, I've tried hundreds of times, and I still use wrong words for these things. We'll come to those. I'm just warning you that null is a very dangerous thing, and everything has to be done very carefully when vectors are null. Time-like are by comparison much easier. Good. Now, once we have vectors, there are some natural quantities. The divergence, del dot V in invariant notation, but it's actually nabla mu, mu. There's the curl, which is curl is normally normally defined on things with lower indices, and it has a wonderful property that the affine connection terms vanish, cancel between these two terms. So here you can actually use ordinary derivatives. That's very helpful. And there's one more, shear, which takes care of the rest. So once you know the divergence and the curl, the only part of the derivative you don't know is the symmetrized one minus the trace part. I have defined shear with a half. I've been quite stupid. I made a mistake already. It's not a half. Okay, half is there, but it's not traceless, right? There should be a 1 over d. Now it's traceless. I think I forgot that in my notes. This is traceless, right? If I take the trace, these two terms with the half give me del dot v. This is del dot v. Trace of that is d, cancels d. So this is traceless. Good. Okay, that's vector fields. So why are we discussing these things? Again, I said we are field theorists. I don't know for a fact that you are, but I am. And fields which describe things like physical particles like photons and gluons and W bosons, they are all, they can all be thought of either as vector fields or as one forms. There was a time in my life when I thought that the only correct way to describe a Maxwell field is as a one form, but turns out that equations of physics are not so kind. You actually need to consider both the raised and lowered versions. But in vector fields, the raised one is the natural one. So the in principle definition starts with a component V upper mu because it's contracted with del by del x. There's a analogous object where the basic quantity has a lower index. So here let's call it W is W mu dx upper mu. Now again, this dx looks like an infinitesimal amount of x, but that's not really its mathematical definition. But for a physicist, that's good because this also transforms under change of coordinates by the chain rule, an infinitesimal amount of x. Always remember, the coordinate x does not transform as a vector. The coordinate x is not a vector, it's a coordinate. But an infinitesimal shift of the coordinate is a vector. Okay? This is a subtle fact for those who have never seen it before. It's because on a generic manifold, something which has a direction has to be based at a point and also point somewhere. Okay, and the coordinate doesn't do that. The coordinate just tells you the name of that point. But if I compare the coordinates at two neighboring points and subtract them, I get dx, and now that behaves like a vector. And because of that, the quantity multiplying it has a lower index. So now its transformation is inherited from the chain rule on that. So differential forms are nice for that. They have many nice properties, and I won't list them here, but now I will get to something maybe more non-trivial and which you probably may not know. So I guess the only thing to add is there is something called the exterior derivative, which arises very naturally here, which is a d, it's called d. It maps, so this is called a one form. I should have said not all differential forms are one forms. A general differential form could be called a P form, and it would have many indices. And the idea here is that we introduce a wedge, what is called a wedge product. Again, it's not supposed to mean anything for us. It's supposed to be a formal product which has the anti-symmetric property built into its definition. So, because of this wedge product, this P form is automatically anti-symmetrized. Okay, so any tensor which has symmetric or non-anti-symmetric lower indices cannot be written as a differential form. So there's a certain specialization involved here, but it's a very useful one. For example, the Maxwell field strength tensor F can be written as a F mu nu can be written as a differential form just by multiplying it by these formal objects and putting a half here.
There has to be 1 over factorial P.
Yeah, that.
To compensate the overcounting.
Yeah, that's up to you. I mean, the point is you can put it or not. That's here I have put it because f has two terms. Okay, so this half reduces it to one term. So this is actually del mu a nu times dx mu with a 1 in front. So when we say a differential form, okay, I mean I think to some extent it's up to you. If we use it, we'll talk about those factors. Okay, but the important thing is that if D acts on a form, so let's say D acts on W, which is equal to that, it sends it to del nu W mu 1 to mu P, Tx mu 1 to dx mu P, wedge dx nu. So this is called the exterior derivative, and its job is that when it acts on a P form, it differentiates the component and puts a dx at the end, which means that after differentiating, it has anti-symmetrized this index with all p indices. So the result is a p plus 1 form. I think if you want to look up my lectures on differential geometry for physicists, all the factors and everything I explained there. There's a playlist, it's on my YouTube website. Good. Okay, now this has all been a little dry and I apologize. It's going to remain a bit dry because we are not discussing physics. We are discussing the objects on space-time in terms of which physics can be formulated. This is the analog of starting a quantum mechanics textbook, as Shankar does, for example, with one full chapter on Hilbert space. It has to be done. It's not the most exciting way to start learning a subject, but it has to be done. In any case, you already learned some of the physics, so it's a nice exercise to try and place in context many things you already know in terms of this kind of notation. Good. Now comes something non-trivial, and I think this I can do and all of you may not know. So I'll just pause for questions, but let me write this before I forget. So we are going to discuss the construction of, sorry, this is the wrong Lorentz. Some geometrical objects which will change the formalism in which we write things, and in fact it's very, very useful in gravity, in the physics of gravity, to express things better. For example, the Kerr metric derivation, which I told you I went through for 2 months, it's 25 pages long. It relies very heavily on this formalism, and a few other things we do will rely on it. So first, the notation. I'll call them local Lorentz frames, and for short I'll call them Vierbeins. So these are the old names, not used necessarily anymore. It comes from the German. Vier is four, Bein means way, so it's 4 ways. So these are some 4-legged objects. The British, trying to avoid German usage, went for tetrads, which also means 4. Tetra is 4. I think it comes from Greek, but they didn't want to use the German one for maybe obvious reasons at that time. So they used tetrads. So Penrose and Hawking's work is littered with tetrads. Problem with tetrads is that we of the string theory generation don't want a different word every time we are in 6 dimensions, 10 dimensions, 11 dimensions. This is very specific to 4 dimensions. Viel means many. It's a German word meaning many. So this will work in all dimensions. People also use Zweibein for 2 dimension, Dreibein for 3 dimension, but it gets really nauseating. So this is one word. Frames, I like to use just frames, but it means local Lorentz frames. So what's the idea? Okay, so given a d-dimensional manifold, I said I would pause for questions. Are there any questions on vector fields and differential forms? I should apologize because I didn't really do it. I just kind of went on a rampage through the subject in few minutes. If anyone has not seen it before, this won't have made any sense. But there was a lot of nodding going on, so I think everyone has seen it. Okay, if anyone really is challenged by all that, then talk to me or look up that course on differential geometry for physicists or some other reference. Because that is stuff that I don't think I should spend too much time reviewing. From here, I think I'll be telling you things that might really be interesting. Okay, so given a d-dimensional manifold, let's choose. Oh, very good. I forgot one notational thing. M. The tangent space is denoted TP of M. I should say the tangent space at P. P is a point, so this is TP of M. I'll make one little comment here. When we want to do anything with a point, we'll have to tell you the coordinates of the point. But if we don't want to do anything with the point and just be abstract, we'll just call it P. Okay. The nice thing is that now if I change coordinates, P is not going to do anything. P is that point. It's that actual point has nothing to do with how I describe it. That's why it's often very useful, and it's useful to remind oneself, because we get very confused. Maybe not you. I get very confused when x mu changes to x prime mu. Am I in the same place? Am I supposed to move every time someone changes my coordinate? No, the point is the point, and coordinate is how you describe the same point. So the tangent space at P is a well-defined thing, and it's nothing but the linear span. It's a vector space. So of all vectors at that point, where vectors we defined before, we defined vector fields. So if you have a vector field, you can take its value at a point P. You can find its the coordinates of that point in your coordinate system, take its value, and then take the linear span of it, and you will get TP of M. Now here's a nice thing to keep in mind. A vector is an infinitesimal thing. It's, as I said, it's a point and a direction moving a little away from it. But once you are in the tangent space, you can have as large a vector as you like. The point is, this is a curved manifold. If I draw a long line, it's not going to sit on the manifold. But if I construct an imaginary flat space, like a plane, which only touches the manifold there, and I insist on working in that space, not in the manifold, then I can take these vectors and make them as long as I like, add and subtract them, reverse them, do any other operation, and everything will work because I'm in a flat space and it's a vector space. So the tangent space is a vector space, unlike the manifold. Very important to understand that. So it's a vector space. So it has all the properties of vector space. You can add vectors, you can multiply vectors by a constant, no limit to how big the constant is, and you'll still get another element of the tangent space. Was that clear, by the way? I mean, again, some people are nodding, but some people are now looking a bit annoyed. So I think we should have questions if that point is not clear. Basically, the tangent space is an artificial construction which associates to a manifold a Euclidean space at every point of that manifold. That is my choice. The manifold doesn't have any Euclidean space living in it. It's something, imagine a sphere. I take a piece of paper, which is a plane, and I glue it on one point of the sphere. Unfortunately, in this example, it looks like I need to live in a higher dimension to make the tangent space, but I can define it intrinsically. I don't need any higher dimensional geometry. I have some manifold, I take a point, and at that point I construct a Euclidean space of the same dimension as the manifold, and in that space I allow these infinitesimal tangent vectors of the manifold to live, but now I allow them to behave like proper vectors, and they can be as big as they want. You might realize right away that the tangent space of Euclidean space is Euclidean space. That's why we never worry in Euclidean space whether a vector is small or big. It could be as big as you like, can be from there to there, but on a curved manifold it can't be actually. So I have to have an auxiliary space to let the vectors live, and that's the tangent space. Good. So now, and I have the linear span of all possible tangent vectors, so it will be d-dimensional, but as you know, in a d-dimensional vector space, I don't need all possible vectors, I only need d linearly independent vectors. So let's pick d linearly independent vectors. One little thing before we do that, tangent space, also I can consider. So let me first state why this is too limited. This is all associated to a point. Okay. What if I have things which vary over the manifold? What am I supposed to do? Tangent space is at a point. If I have another point, there will be another tangent space there. I can't add vectors in this tangent space and that tangent space. That's simply doesn't make any sense. They are different spaces. What I can do is to take the union over all P in the manifold of Tp of M. This is actually called the tangent bundle. So it's not a vector space anymore. It's only a vector space for any particular point, but now it runs over the whole manifold. So it's like all tangent spaces considered together. And now the idea is very nice. Supposing on this manifold, which I'll depict like this, I find a basis like this of, this is my point P. I find an orthonormal basis, just like I do with ordinary geometry, ijk unit vectors, okay? But I also allow it to move continuously, smoothly, even differentiably all over the manifold, okay? So this is the basis here, but at some point P prime, which is close by, I specify the basis. It's not unique, I have to specify it. But I would like that as we go from P to P prime, this kind of gradually turns into this. It doesn't do any weird things. It doesn't cease to exist. It exists everywhere and it's smoothly defined all over the manifold. Okay? So this is the idea of frames. So we take a basis of smooth vector fields on M. A vector field, as I already showed you, is something that is allowed to vary all over the manifold. And as I said, maybe I didn't emphasize, but meant to be smooth, smoothly vary, meant to be differentiable also. Later in the course, we'll talk about the smoothness and differentiability in more rigorous detail. But here we can be a little lax about it, just they should smoothly vary. Okay, so I want a basis of smooth vector fields on M. So how many such vector fields should there be to make a basis?
Dimension of the
Dimension D.
manifold.
Yes. So let me call these vectors EA, where A is an index which again runs over 0 to D minus 1. But it's not a coordinate index, it's just a label of D different vector fields. By the way, some authors actually label this from 1 to D. Wald, for example, but it's confusing. I think we should, since it's a pseudo-Riemannian manifold, this is a more natural label. These are functions of X, and they are all vector fields. Okay. Now, if EA of X for fixed A is a vector field, I should be able to write it as a component times del by del X. That all vector fields look like that. So I can write it as EA mu upper of X del by del X mu. So this is a basis. Okay, and note that the components have D squared indices because D of them are the components of the object as a vector and the other D are the label of which one is the basis vector. It's very much like XYZ. Okay, if you remember your ijk vectors, you can call them EA where A goes over 1, 2, 3. But each vector has a 3-component description, right? Like 1, 0, 0, or in some other coordinate system it might be anything. So it has 2 indices. So these are the components of the vector fields. Now, what do we normally do when we define bases? We make sure that they are orthogonal. 2 of them are orthogonal. We don't have to, but like you would be a fool not to, because that makes them simple. That's why they are most useful. We make them orthogonal to each other and we make them have unit norm. Okay. Now here, unfortunately, because we are pseudo-Riemannian, we have to do something analogous. So so normally 2 of these, their dot product would be delta AB in Euclidean space. What would you think it should be in a Lorentzian signature spacetime? Eta. Exactly.
Metric of SO1, D.
Exactly. So E A So let's write this non-statement as, if I don't put the second index, then it's the vector field. So here's an abstract non, but to define it concretely, it's G mu nu, E A mu, E B nu. Because norms of vector fields we already defined, they are all defined with the metric. Okay, and what I want this to be, I demand, is that this is eta n. This is the strict analog of taking a ordinary curved space, having an orthonormal basis of frames, and the orthonormality condition is that this is delta A. So this technically this is not orthonormal, but it has an invariance. Orthonormal things have invariance under rotation. Okay, this will have invariance under what you said, the Lorentz group. So this is Lorentz invariant. If I make a Lorentz transformation on all my frame, on my whole basis, the inner product will survive exactly the same. And that's good, because if I chose anything else here, that wouldn't be true. Remember that eta is the unique constant tensor which is preserved by acting with lambda, and so lambda, eta, lambda transpose equals eta, where all of these are matrices. This is the definition of the Lorentz group. Good. So I have these frames now and I have defined them to be orthonormal. And now something interesting happens. E A mu has two different important transformations. If I perform a general coordinate transformation on the manifold, then this index is not affected because this is the label of the frame, but this index makes it transform like any other vector field with upper index. So it goes to E A mu prime of x prime. Probably the first time I'm actually writing this out for you. Okay, and note that x has gone to x prime and this has also become a new function. That's exactly how vectors transform. That's one key property, but the second key property is that this is under general coordinate transformation, which I'll call GCT, which also can be called reparametrization. General you can be called diffeomorphism. No, we don't use general, we just say diffeomorphism. So any of the above. But there's a different transformation which I call LL, which stands for local Lorentz, in which E A mu goes to E prime A mu. Now x does not change because I have not reparameterized the coordinate at all. It's the same x. But the function has changed, and how has it changed? It has become lambda AB EB mu of x. Nothing has happened to the mu index either, and this is the Lorentz transformation matrix. The one which satisfies that equation.
Sorry, this lambda also depends on x, right? Local.
Lambda does depend on x. Well, the point is that I can make a local Lorentz transformation independently at every point. So in that sense, I can choose lambda to depend on. So this equation, first of all, is true at a fixed x. But now I can make this true at all x. I mean, it will be true at all x. And so lambda will eventually depend on x. So in the first case, the transformation was x mu goes to x prime mu of x. In the second case, the transformation is not on x at all. It is just a rotation of the frames. It is E A mu goes to lambda AB EB mu. Now, if you think a little bit as a field theorist, there's a crucial difference. This is what we call a space-time transformation. And this is not a space-time transformation. I'm doing nothing to space-time. I'm simply rotating my arbitrary choice of frames. So I already made an arbitrary choice, and now since I've made it, I can rotate it, and this is the correct way to rotate. The key thing, that's all of these formulae are well known in Riemannian geometry, except that this will just be an orthogonal matrix, and all etas will be replaced by deltas. Okay, so I have frames and I have their transformation properties under the Lorentz group. There are more details in the notes. And now I can also define one forms from them. So these are vector fields, of course, by definition. The frames are start out life as vector fields. But I can also make them into one forms by just defining A lower mu as G mu nu E A upper nu. I lowered the index. Note that this is non-trivial because I have put a whole function. Everything is a function of x. So the relation between E upper and E lower is quite non-trivial thanks to G. But whatever it is, there's that. So now I can ask all kinds of questions. Also I can do one more thing. I can, instead of writing E lower A upper nu, I can raise the A index from down to up. Now normally that shouldn't be a big deal because it's a frame label, but because the transformation acting on these is the Lorentz transformation, I must use the Minkowski metric to raise it. In this case, this is constant all over the manifold, and it just has the effect of raising this, and what it actually does is does nothing on the space index on the indices from 1 to d minus 1, but if this index is 0, then there's a change of sign because of the Minkowski metric. So I can do this, and I can do the last one, E upper A lower mu, by just using eta to raise this and using G mu nu to lower that. E, B, nu. So I have 4 different E's, both down, both up, one down, other way around. Okay, and they are all related in straightforward ways. And there are 2 nice inner product formulae. One of them I think we already had, which is that one. I'll write it again. But there's a associated formula which says that if I take E A mu E B mu and E A mu E B nu eta A B. So here what happened is I contracted the mu and nu indices with G. Now I take these two and I contract the A and B indices with eta. So the result has only mu and nu, and it's an exercise for you to prove that this is G mu nu. So we conclude that the frames, this is a commonly used thing, are square root of the metric. It's just words. Because after all, take the det of this det is 1. Let's take mod det, so we don't care about signs. Det of this then is 1. Det of this times det of this, which is square of det, that's det of G. This is the sense in which frames are square root of the metric. And amazingly, although this construction should have been known for many, many decades, it was only in the supergravity years that people started to write this. And there are even, if you Google, you'll find people like Peter van Nieuwenhuizen wrote, supergravity is the square root of general relativity. It was a bit over the top, frankly. Actually, it's at some level, it doesn't make much sense, but it's this statement. Because this turns out to be the basic field in supergravity. Again, if you don't know this, don't worry, that's something that will emerge. I'll soon do how to couple fermions to gravity, and then you'll see exactly what I'm talking about. Okay, are there any questions?
So these beamlines will automatically inherit any of the isometries that the original manifold had?
Isometries. What do you mean by inherit an isometry? Isometry is a property of a manifold.
Yeah, so I mean, for example, rotation, eta AB is invariant
not rotation but Lorentz transformation. But see, that's nothing to do with symmetry of the manifold. Any manifold, its tangent space has Lorentz symmetry. Any manifold, even manifolds with no isometries. So it's not a statement about symmetry or isometry. It's just a statement about the manifold being a manifold.
But then if I want to, let's say, create a beam which is invariant under any arbitrary group action, is that possible?
But it's not invariant. It transforms under local Lorentz transformations. Because what am I doing? You see, isometry is a direction of along the manifold where I feel that I have not gone anywhere. I'm not experiencing any change. But local Lorentz transformation is we don't go anywhere. We start at P and we finish at P. We simply take that basis of three things and we do that to it. That is a local Lorentz transformation. We are not going anywhere. We are not exploring any part of the manifold. We are just where we were. It's very different. But there's a little bit of a shock, therefore, that somehow we can use it to simplify how we think about general relativity, and that's why I introduced it at all. It's extremely weird, but true. Suppose we have a field. Imagine it's a Maxwell field, A mu of x. Now, if it's there in a general relativistic system, then you know very well that under general coordinate transformation, this goes to A mu prime of x prime is equal to del x nu, del x prime mu, A nu of x. Right? Now, let me define. So this is the Maxwell field and this is how it should transform if I'm in a general relativistic system, and that's called the Einstein-Yang-Mills system, very common thing to study. Now I'll define a field A of x, which is defined to be E A mu of x. This definition is frame dependent. First I have to choose the orthonormal, the local Lorentz frames, then I contract them with that and I get this. Okay? Now the first thing to note is that this is invertible. Very easy to invert because A mu of x is just E upper A mu of AA. Easy to verify. Because we already saw that EA upper mu and EA lower mu are essentially inverses of each other because their dot product is eta AB. Okay, so it's invertible. Note that the new object AA has no space-time indices. So AA is a set of D scalars with respect to spacetime. Each component for A varying from 0 to D minus 1 transforms as a scalar. How did this miracle happen? I've converted all my vector fields to scalar fields. If you have struggled through Maxwell theory and all its complications, you would find it utterly bizarre that I can take a vector field on a manifold and transform it into D separate scalar fields. Of course, there's an obvious reason. This is not A, but it's A dotted with my choice of frames. And what happens is that every time there's a general coordinate transformation on that, it also acts on the frames in an inverse way. That cancels out, and therefore the result is scalar. But because the frames carry this extra index, this thing transforms under local Lorentz transformations, which the original mu did not. So it is a local Lorentz vector. So it doesn't take much to guess what that means. That means that under local Lorentz, AA goes to lambda AB, AB. But something has been achieved because it looks like I have flattened my manifold. This is a formula of special relativity. This is also how the photon field transforms in special relativity, where I'm free to confuse A with mu, because the metric is just eta mu nu anyway. G mu nu is eta mu nu. So then there is no real difference between the A and the mu index. This is special relativity. That equation above the boxed one is general relativity. Somehow I've got rid of that and I've got this. Fantastic. But as I said, the hidden price is that this has this A index and the frames are doing their job, okay, because I have defined that auxiliary system and they encapsulate all information about the manifold. So in a way, by defining AA as in that box, I allow the frames to take away that information and replace it with local Lorentz transformations. Are there any questions about that? It's all described in a lot of detail in the notes. Okay, 5 minutes to go. Let me give you an example. I think examples always help. So, let's consider a manifold of this form. A manifold whose metric is minus, in some coordinate system, is minus f of r dt square plus h of r dr squared. As you know, the Schwarzschild black hole is a special case of this, plus r squared d theta squared plus sine squared theta d phi squared. So 4D manifold, 3 plus 1D manifold if you like. Okay, so that's a metric. And now I have to define 4 frames. So let me define, now I can define them either as vector fields or as differential forms. Remember that as differential forms, they have a lower mu index, which is somehow useful because the metric has 2 lower indices. Okay, so I'll write them as differential forms with their label up. So E0 mu. So I have to write for you E0 mu dx mu. Okay, and this I'll call EA. Some books, this is a bit confusing because from this you don't really know if I'm talking of EA lower mu dx upper mu or EA upper mu dx d by dx lower mu, the vector field or the differential form. But hopefully from context this makes it clear. Okay.
This is E0.
This is EA, sorry. For now I'm going to write them. So E0 I'll choose to be root of f of r dt. That means if I look at E0 upper 0 lower mu, it has only a 0 component and then the others are vanishing. Then E1 I'll choose to be root of h of r dr, I guess, and then E upper 2 is r d theta, and E upper 3 is r sine theta d phi. And of course, what you're thinking is that this was very easy because my metric just had no cross terms. There were no dr, dt's or d theta, d phi's, so I could do this. Well, it's an example. If it's more complicated, it may take you more time to find these. Or what you might want to do is to take a complicated metric, find a coordinate transformation if possible to write it this way, and then look for the frames. It's up to you. But this is just an example. And you can, in this case, a nice exercise is to, so these are one forms. So exercise is write E A mu L by del x. So what you have to do is use the metric to raise these. It's very easy. Okay. But now, and this is the last thing I'll do today probably, now finally there is a real question. What if we differentiate? So I can differentiate it by just writing del mu AA. Okay. Now I have an interesting problem. I said this is a set of D scalars. You know that when we act on scalars, the derivative is just ordinary derivative. There is no Christoffel symbol in it. Okay. And yet this cannot be a Lorentz vector and a space-time vector, because the Lorentz property gets destroyed by differentiating. Why is that? If you recall how it transforms, you'll see immediately. Transformation is local. AA goes to lambda AB of x times AB. So when I differentiate, sometimes the d mu will act on the A, sometimes on the lambda. So it's not LL anymore. So it is now a set of vector fields, vectors or one forms as in this case, but is no longer LL, which it was. So this is not the right derivative to perform on something with a local Lorentz index. So there has to be a rule for that, and the rule is that we change the definition of our covariant derivative. Earlier the covariant derivative had a rule. Whenever it sees a space-time index, it puts a Christoffel symbol once for every space-time index and sums up. That rule is known. But we add a new rule which is embodied by this, that this is ordinary derivative of this plus a new object omega mu AB AB. And this is a new type of connection, and there is supposed to be one of these for every local Lorentz index. So in general, if I differentiate an object which has many local Lorentz and many space-time indices, I'll have one Christoffel for every space-time index and one, this thing, which has a name, it's called the spin connection. For every local Lorentz index. And how do I know what is this weird object? Well, my requirement is precisely that given AA was a
This index has been mismatched.
mismatch.
So A should be downstairs.
It doesn't really, sorry, this should be up, well, this should be down. So actually A and B indices up and down, of course they may affect by minus signs. They can't make things go wrong other than with minus signs, because all the raising lowering of those indices is done by eta. Good. So this is a 3-index object, much like the Christoffel symbol, but here one of its indices is space-time and two are local Lorentz. Okay. And we can easily derive, there's a nice proof that this has to be antisymmetric as follows, that omega mu AB, now I am looking at the one where both indices have been lowered just by using eta. This is antisymmetric in its second two indices, and there cannot be any symmetry with the first index, which is of a completely different kind. Okay, this is an exercise, it's proved in the notes. Good. Now, I can easily find a formula for this covariant derivative on the frames themselves. What is this? Now you have all the rules. First, it's as an ordinary derivative term. Then it has a term which has a spin connection and rotates this index. Then it has a term which has an affine Christoffel symbol acting on this index, which is minus gamma mu nu lambda a lambda. So it has three terms. And then you can easily verify that because a came by contracting this E with the original vector a mu, that the ordinary covariant derivative on the original a mu and this covariant, these are all compatible, three different things, but this is like the most general definition. Having this in mind, you can take any number of a's, any number of mu's, and you can take upper and lower indices for these. For this you need not, because you can always lower indices for free. They never, there's no space-time dependence is ever introduced by raising or lowering local Lorentz indices. Good. Okay. Now it so happens this has a name, but it's slightly different from what I was asked earlier about torsion. This object has a name T mu nu and it's called the torsion tensor. It's a specific definition in the context of frame. So this is actually what mathematicians know as torsion. Okay. And the last thing I'll say, then I'll stop, is that since this is a tensor and we don't know what to do with it roughly, or if you like, choosing it gives me a special class of frames. These are my choice, the frames. Okay, so if I am able to choose the torsion tensor in a convenient way, I should do it, and I simply set this torsion tensor to 0. This is known as the Feuerbine or Feuerbine postulate. It's not really a postulate. It's a property of this which we can set to 0 consistently, and if we do, and if we are clever, you'll see that we can take this equation, this being 0, and solve for omega mu ab, and we'll get an answer for omega in terms of e's. So omega is determined by e's in the same way that Christoffel is determined in terms of g's, the metric, but it's not the same formula. And next time I'll show you that this turns general relativity into something that looks exactly like Yang-Mills theory. Quite remarkable, where the gauge group is role is played by the Lorentz group. Okay, I'll stop here. Sorry, went on a little bit. Any questions? Okay, very quick poll. This was too hard, too easy. Please give frank answers. So first, too easy. Alright? Come on, somebody.
Not too easy, but
Okay, somewhat easy. Okay, few more
Mostly
people.
known.
Huh?
This was mostly known, sir.
To you, but I don't know.
this is written in your book, this topology.
Well, but if you don't open the book, then you won't know it, or some book. So I'm just asking whether it's known to this audience. I think there are people who did not know this and don't want to say, but you should say, yeah. So this is new, somewhat new to people? Okay. No, this is TIFR. You should be much more frank. Huh? Please, I'm expecting it from you. This is sort of known, sort of not known rather. Reasonably not known, reasonably new. Interesting enough that, new enough that it was interesting, not just repetition of something you knew. I'm trying to gauge how hard people are finding this, and I'm not getting a very good feedback. Okay, I'll also give, from time to time, I'll give some polls on the web page. Okay, good. We'll continue in this spirit next time and also start on geodesics.